I'm Andrew Villadsen. I'll be talking about ant systems, a family of swarm intelligence-based algorithms, and their application to approximate solutions of the traveling salesman problem. First, let's review the traveling salesman problem. The traveling salesman problem is to find the lowest cost circuit visiting every node in a weighted graph. In principle, standard search algorithms such as A* can be used, but the size of the search space makes this impractical. In fact, the traveling salesman problem is NP-complete, which means there is likely no efficient way to compute an exact solution. In practice, though, we usually don't care about having the best solution. We just want a good approximation, and with that relaxation, there are a number of efficient algorithms, including ant systems. First off, what is swarm intelligence? Swarm intelligence is a large number of similar, simple agents working together to solve a problem. Each agent follows simple rules, but as a group, they exhibit sophisticated behavior. There are many examples of swarm intelligence in nature, including neurons and the flocking and schooling of birds and fish. Ant systems, as you might guess, are inspired by the behavior of ants. Ants in particular achieve swarm intelligence through stimergy. In short, stimergy is the practice of communication through signs of the work that has already been completed. Instead of directly communicating, agents observe signs left behind by other agents and react accordingly. This has the advantage of being highly parallel, since agents not only don't require central coordination, but also don't even have to directly communicate with each other. Before returning to the traveling salesman problem, let's talk through a simplified example of how real ants solve pathfinding problems. After finding a food source, ants need to establish an efficient route to that food source. They achieve this through the use of pheromones. Each ant lays down pheromones as it moves. Ants move randomly, but prefer to move along paths with higher levels of pheromones. Pheromones evaporate over time, which as we'll see results in shorter paths having higher densities of pheromones. Over time, the positive feedback loop created by the pheromones results in almost all ants taking a shortest path. Let's work through a simple example with one longer path A and a shorter path B. At first, there are no pheromones on either path, and about 50% of the ants follow each path. However, because B is shorter and takes less time to travel, each point along B is visited more frequently than each point along A. Because the pheromones at each point along A are refreshed less frequently, evaporation has more of an effect on A than B. Eventually, the ants observe more pheromones along B and begin to prefer that path. This preference means that the pheromones along A are refreshed less and less frequently, and eventually almost all ants travel along B. Finally, we can return to the traveling salesman problem. We find an approximate solution by modeling ants traversing the graph and laying pheromones along the edge of candidate circuits. Finally, the ants are organized into generations, with the ants in a generation using the pheromone levels from after the last generation. This makes modeling the ants within a generation highly parallelizable, since the shared resource is read-only. Each ant traverses a circuit, choosing a random edge at each node, but preferring edges with higher levels of pheromones. Ants also lay less pheromones on longer paths, mimicking the result found with real ants. At the end of each generation, the pheromones from the last generation are reduced by a fixed ratio, and then the pheromones from the recent generation are added. It turns out, however, that the ant system I just described, which sticks very closely to how real ants work, isn't very good. In particular, it suffers from a lack of focus. Early generations may discover multiple, very different short circuits. The pheromones don't distinguish which path they were from, so instead of refining the previously discovered solutions, ants often confusedly combine the solutions in bad ways. The issue is addressed by only having the shortest circuit from each generation lay down pheromones. This focuses the ants on refining a single solution. However, focusing on a single solution introduces its own problem. The ants may be refining a local optimum that is much longer than the actual shortest path. This can be mitigated through the introduction of negative pheromones, which discourages ants from following edges. Negative pheromones are laid down along the longest circuit from each generation. The longest circuit from each generation is usually fairly similar to the shortest circuit due to the focusing effect of the positive pheromones, so this encourages ants to explore further afield for better circuits. Thank you for listening to my presentation. For those who are interested in learning more about ant systems, Here are a couple papers about ant systems and the traveling salesman problem. This presentation summarized at a very high level the techniques found in these papers.